Hello, my name is Virgil Kohlberg, and this is my Physics Lab 2 on changing velocities. So as an introduction, for this experiment we're going to try and demonstrate the effect of forces on an object, on a falling object. So to understand this, we need to understand Newton's second law of motion, which states that force is equal to mass times acceleration. So we can see that force is proportional to acceleration. So on a falling object, two forces will be acting on this object. First of all, there's the gravitational force, the acceleration g, of the Earth on the object, as well as drag, which is the air resistance acting on the object. All for this to work, we need to work with vectors. All of this is happening on the y-axis, but the gravitational acceleration and force will be negative, while the drag is positive in regards to that axis. We will see that from this experiment that drag is a non-negligible force which can be predicted through computational models, but not all of them, ones who apply a drag force in its computation. Here are some relevant formulas and values. We have the velocity update formula and the position update formulas, which depends mostly on Fnet, which is the sum of all the forces acting on this, or the vector forces acting on the falling objects, which are here gravitational force and the drag force. And for g, the gravitational acceleration will take 9.81 as the value. So here is my experiment. So as we can see, my system was a paper plate that I dropped from 1.75 meters high, recording its position at regular time intervals. And we can see that the surroundings is mostly the air acting on the system, so on the plate upwards, and the Earth, of course, which was accelerating the plates downwards. I plotted here the y position over time, and as we can see, it is a non-straight line. So here are my experimental results. We can see it took 0.8 seconds to travel 1.75 meters, and once again we can see that it is not a straight line like it would be if there was no acceleration. As we can see, the gradient is increasing in magnitude, meaning that there is an increasing velocity, hence an acceleration acting on the object. Here is the simulation with only gravity. As we can see, the time was set to 0.801 seconds, as was during the experiment, and here is the ball velocity update and the ball position update, which we can find here, which is minus g is just Fnet over m rewritten, and g here is the same thing, Fnet over m delta t and delta t, or it's just delta t squared, as we saw from the position update formula. And we can see that it gives us a polynomial curve here of constantly increasing negative magnitude of velocity throughout the fall. So here is the simulation of gravity with drag. So once again, we can find that t is up to 0.801, and we see that the Fnet, the force now has an impact. The force is the force of acceleration plus the force of drag. So the force of acceleration, of course, is a negative value, while the force of drag is a positive one. And we can see that from here that the constant, the drag constant, is a 1.25, which is the value that best matched the real life example. Here, once again, we have a velocity update formula and a position update formula, this time in terms of Fnet. And for all of this, we assumed that the mass of the paper plate was of 1. So here is a comparison of the different curves. As we can see, there is the one with only gravitational acceleration is constantly accelerating, almost to infinity. Now we can see that the one with gravitational acceleration and drag is slightly, has a slightly lower velocity than overall average velocity than the real life example. This is mostly because the real life example is not in a perfect curve. As we can see, the values vary up and down slightly due to human error, due to the camera being slightly angled. We can see here that with the position update formulas, Fnet are these values. So this one is with only gravitation, and this one is with gravitation plus drag. So as an extension, we have to talk about the what if, what does it mean, the terminal velocity. So as we can see that the gradient of the curve is flattening out when there is drag. We can see here the gradient is slowly getting to a constant gradient, while with only gravitation, the gradient change remains constant throughout the fall. And we can see from this velocity over time graph that the curve is slowly flattening out, and we can assume that at some point we'll reach a constant value, meaning we've reached a constant velocity, which means that the force due to acceleration and the force due to drag will cancel themselves out. So now, what if the object did not start at rest but started in motion? Well, when the ball is released, the net force acting on it is the same. One has just a higher velocity. So that means that both will reach the same terminal velocity because the forces acting on it are still exactly the same. The only difference is that if it starts at a higher velocity, in this case at -1 meters per second instead of 0, it will reach this terminal velocity quicker than if it started slower. As you can see here, the curve started flattening way earlier than with this graph. Thank you very much.